Hi everybody, and welcome to my video on the ratio and the roots test. So the ratio and the roots test are going to be two types of tests that we can use to check for convergence of a series, and it's going to be a little bit different than some of the other convergence tests that we've been looking at. Here it's kind of illustrating when we want to use a ratio test. So here, ratio test obviously is going to test for what's known as absolute convergence because we're taking, say, the limit of something as an absolute value. So as we take something as an absolute value, that's where we get the term absolute convergence from the absolute value. It's used for something that is can use to be shown that it's going to converge quickly, or for some of the more complicated types of series that you may see. And for example, series that involve factorials or exponentials, those are two key terms that we need to make sure that we're recognizing. Factorials or exponentials are typically going to be well suited for the ratio test. And we'll take a look at the root test here in a little bit. And towards the end of the lesson, we'll kind of have a general recap of some of the different types of convergence tests that we've seen and when it's going to be a good idea to try to use them. So here it's kind of illustrating what the convergence, or how you test for convergence with the ratio test. The series is going to be a series of non-zero terms, obviously. The convergence, absolutely. The absolute convergence is going to show if the limit of the ratio of a sub n plus 1 over a sub n is less than 1, meaning that it's going to be some number like 0, or it's going to be some fraction between 0 and 1. That's what we're going to use to show that it's going to converge absolutely. If the limit is going to be something greater than 1, it's going to show that it's going to diverge. And if the limit is exactly equal to 1, in those rare instances, that's where we're going to show that the ratio test would be inconclusive. Now the ratio test, in a lot of instances, because we're going to be looking at something that is going to have something that could be as an exponential or something as a factorial, we may see, some kind of a series, that just makes something up here, 3 to the n power over n factorial. That might be something where we want to apply to use the ratio test. Now, if you notice, the ratio test obviously is going to take something over something else. So in the example that we have, I would say something like the limit as n approaches infinity of the absolute value. So here, a sub n plus 1 is going to just add a 1 anywhere I have an n term. So I would have 3 to the power of n plus 1 over n plus 1 factorial. And all of that is going to be over some other, the original term, which would be 3 to the n over n factorial. So here, essentially, we're dividing by we're dividing two fractions, so we could also take a look at the expression and say that the ratio test can be performed this way, where we say the limit as n approaches infinity is going to be the expression a sub n plus 1 times the reciprocal of a sub n. We can write it like that, and this is going to be my preferred method of doing it simply because it'll save us a step from taking it from the complex fraction that we have to being a more simple multiplication problem. So here, determine whether the following series will converge or diverge. These are going to be three examples that are going to show us one where it will show us it's going to converge, absolutely, one where it's going to show us that it will diverge, and we'll see one example where we would show that it's going to be inconclusive because we'll have a limit of 1. Okay, so this example here on A is very similar to the one that I just did, that I just kind of made up. So the way that I'm going to look at this, and this is going to be the only one that I'm going to set up this way, where we actually do the ratio test. as an actual ratio itself. So if I want to look at this and say, okay, using the ratio test, can I determine if this is going to be convergent, divergent, or inconclusive? I'm going to start it off by saying the limit as n approaches infinity of the absolute value of a sub n plus 1, which in this case would be 2 to the n plus 1 power, divided by n factorial would become n plus 1 factorial, and all of that's going to be divided by a sub n. So this whole thing in it that was given to us, that is a sub n. So I have 2 to the n power, and that doesn't look very much like 2 to the n power. 2 to the n power over n factorial. So let's get our absolute values going all the way down. So when we divide with a fraction, we're really multiplying by its reciprocal. So that's usually where I just kind of start the problem. So what I just wrote down, I usually skip and I just kind of go straight to what I'm about to write here, where I would say 2 to the n plus 1 power divided by n plus 1 factorial multiplied by the reciprocal of 2n over n factorial, 2 to the n over n factorial. So that would become n factorial over 2 to the power of n. Now at this point we need to be able to make sure that we can identify terms in the numerator and the denominator that will simplify to be 1, or use properties of exponents that we can show are going to simplify. So I'm going to just rewrite this expression. The rewriting here is not strictly necessary. I'm going to just rewrite the expression just so it's easy to see the terms that we're going to see. So the limit as n approaches infinity of the absolute value. So I'm going to put the n terms first, like the n factorial. So I'm going to have n factorial in the numerator, and in the denominator, the n factorial, or the n plus 1 factorial, can be rewritten as n plus 1 times n factorial. And now we'll put the exponential expressions with the base of 2, and we'll say 2 to the, now here some people are going to do different things. I'm going to just leave it as n plus 1 over 2 to the n power. Now some people here at this point, for this part of the numerator where it says 2 to the n plus 1 power, some people may use properties of exponents and rewrite 2 to the n plus 1 power as 2 to the n power times 2 to the power of 1, just so you can kind of see how things are going to simplify. And doing that, you would see that the 2 to the power of n in the numerator and the denominator are going to simplify, but we can very easily, pardon me, kind of look at it using just basic properties of exponents. I'm going to, instead of looking at it like that, I'm going to just look at it as my normal properties of exponents, where I'm going to say the top exponent minus the bottom exponent, or vice versa, whichever is going to give me a positive expression. So we would say 2 to the n plus 1 power minus, oh, not minus there. We have a common base, so we just subtract the exponents from each other. So minus n, and you'll see that the n's are going to cancel out, leaving you just 2 to the first power. So that's, so essentially I've kind of simplified half of the absolute value expression already, but let's kind of keep going here, keep going horizontally. The limit as n approaches infinity. Now what you're going to see is, obviously here n factorial and n factorial simplify to be 1. 2 to the n over underneath, or 2 to the n plus 1 power over 2 to the n is just going to leave me 2 to the first power. N plus 1 minus n is just going to be 2 to the first power. So, or just 2. So I'm going to have 2 over, and I still have an n plus 1 in the denominator, n plus 1. So we've simplified everything inside of the absolute value that we possibly can. Now we can just look at the expression and say what the limit is going to be. So in the denominator, all we have, that's the only place where n is existing. So as n gets incredibly large in the denominator, a constant divided by an inexpressibly large number simplifies to have a limit of 0. Okay? So the limit in this case is going to be 0. what that allows us to conclude, according to the divergence test, now here, or to the ratio test, I should say, in this case, the limit of the expression was equal to 0, and in this case, 0 is less than 1. Therefore, we can say this series, golly, I can't, where's my head? I am not I'm not an English teacher for a reason. This series will converge absolutely by the ratio test. So we showed that the ratio test produced a limit of 0. 0 is less than 1. So according to the ratio test, we can say that the series 2n over n factorial must converge absolutely. So moving on to the next example here, again, the idea that we have something as a factorial and or something as an exponent is the kind of clue that lets us know we should probably attempt to do the ratio test here. So again, what's given to you, this whole thing, that is your a sub n term. So according to the ratio test, now here I'm not going to actually write the individual ratio or the original ratio. I'm going to just go to the multiplication operation. So I'm going to say a sub n plus 1. So here I'm going to get n plus 1, which would be n plus 2 factorial, over 3 to the n plus 1 power times the reciprocal of a sub n. So that'll give me 3 to the power of n over n plus 1 factorial. Now again, at this point, what I'm going to do is I'm going to just kind of rewrite the multiplication so it's a little bit easier to see what's going to simplify. And we'll use the properties of factorials to kind of simplify the n plus 2 factorial as well as the n plus 1 factorial. So this will give us the limit as n approaches infinity. So n plus 2 factorial, according to the properties of factorials, can be expanded to say n plus 2 times n plus 1 times n. I guess I don't really need that in parentheses, but I'll just leave it since I have it written. And n plus 1 factorial is the same thing according to factorials as n plus 1 times n, or n factorial. And I guess I'll keep that in parentheses because I put the other one in parentheses. And then of course we have the 3 to the n power over 3 to the n plus 1 power. So what we're going to see as we start simplifying, here n plus 1 over n plus 1 simplifies to be 1. N over n simplifies to be 1, leaving me an n plus 2 in the numerator. Now the expression that we're seeing on the right with the exponents with a base of 3, again, I'm going to just subtract the exponents from each other, and that's going to be like in the denominator, that's the larger exponent. 3 to the n plus 1 power minus n is just 3 to the first power, or just 3. So this whole thing simplifies with that, leaving, oops, I didn't want to put that one there. Let's see, there we go. So it's going to simplify with that n, it's going to take care of it, and it's just going to leave me 3 to the first power. So rewriting my limit will give me limit as n approaches infinity. All we have left in the overall numerator is just n plus 2, and in the denominator, all we have is a 3 to the first power. Now here, when I plug in, when I start substituting, when I look at n as it gets towards infinity, the numerator gets indescribably large. So as that number gets bigger and bigger and bigger and bigger, dividing by 3 is not really going to do anything. The limit in this case is going to go to infinity. Okay, So in this case, what we're showing is that the limit, since it is greater than 1, what we're going to be able to say, so this series, according to the ratio test, must diverge. So this series will diverge according to the ratio test. And the next one, as I explained to you kind of when we started this one, this next one is going to show you that when we do have something that will be inconclusive. So I'm letting you know now the limit on this one should equal to 1. So feel free to pause the video and see if you can do the ratio tests independently and show that the limit in this case is going to be a 1. So let's try working it out here. Okay. So I'm going to say, according to the ratio test, I'm going to say the limit as n approaches infinity of n plus 1 over the cube root of n plus 1 times the reciprocal of a sub n, in this case would be the cube root of n over n by itself. Okay? So I'm going to treat this the same way that I did on the last two. I'm going to kind of take the radicals and I'm going to put them in one ratio so it's easy to see. So here the limit as n approaches infinity of the absolute value. So the square root of n over, I'm sorry, the cube root of n over the cube root of n plus 1 can be written as the cube root of n over n plus 1 like this times, and we're going to have n plus 1 over n. And specifically, I'm actually going to want to break this part up in properties of limits. Let's kind of take this and let's rewrite it like this. Let's close the absolute value here and let's multiply it by the limit as n approaches infinity of the absolute value of n over n plus 1, because looking at each individual piece is going to be pretty easy to see what's going to happen. Okay. The first one, the cube root of n over n plus 1, as n goes towards infinity, and again, technically I really should be using L'Hopital's rule because we're going to wind up with an infinity over an infinity under the radical, and as the for the n over n plus 1 ratio, we're actually going to wind up with a infinity over infinity are indeterminate forms. So technically I should be using L'Hopital's rule, but at this point we can recognize that this limit here, this is going to go to 1, this is going to go to 1, so the limit of 1 times 1 is just equal to 1. And so in this case, because the limit of n approaches infinity of a sub n plus 1 over a sub n equals 1, we can say, I want to, not getting my thoughts down here. It's not possible. In other words, it's inconclusive. To tell if this series converges or diverges. So by the ratio test. by there we go. So now we've seen three examples of how to use the ratio test to show if something is going to be convergent or divergent. If the ratio test gives you a limit less than 1, we say it's going to be convergent. If it's going to be greater than 1, we're going to say it'll be divergent. And if the limit actually equals 1, like we saw here, it's inconclusive. You can't tell if it's convergent or divergent. You'd have to pick some other test in order to be able to do that. Maybe, I don't know, maybe the P-series test, looking at it. But that would be one way of trying to do that one. Maybe not the P-series test. We might need to try something else on that one, but we're not asked to do that here. We're just trying to using the root test or using the ratio test, where we're going to get. So the second type of test that we're going to take a look at here is known as the root test, and it's essentially something where you're going to be taking like the square root of something, or in this case the nth root of something. So according to what the information is giving us here, it says here the root test for convergence or divergence works well for series that involve nth powers. Not saying like something to the 5th power, to the 10th power, or whatever like that. It actually says something to the power of n, okay? Because obviously if I take the nth root of something raised to the nth power, they undo each other, leaving me just the radicand. Now, the expressions that we're seeing here for the root test, obviously a sub n is going to be a series, and what they're showing you is that if the limit of the absolute value of the root test gives you less than 1, and we can say just like with the ratio test that it's going to converge absolutely. If it diverges, that means that the limit is going to be equal to 0, and the root test is inconclusive if the limit is equal to 1, just like with the ratio test. Now, in this case, to me, it seems like the absolute value stuff is strictly not necessary because, first of all, with the series, the n terms are going to be positive. Now, of course, it is possible that you're going to wind up with a negative value when you actually perform the root test or the root test. But a lot of times with the types of numbers that we work with in a series, unless it's going to be alternating, a lot of times you're really not going to end up with a negative term. So the absolute value bars that we're going to see there, they're a little, maybe you need them, maybe you don't. Technically you should have them, but as far as your work, if you don't include the absolute value, a lot of times it's really not going to make a difference to the outcome because you're going to wind up with a positive radicand anyway. But anyway, let's take a look at some examples here. So again, we'll see some examples now. In this case, the root test that we're going to be looking at here is not going to be quite as diverse as what we saw with the ratio test. But let's take a look. Here we have e to the power of n over n to the power of n. So since both the numerator and the denominator, even though they're different bases, they're both raised to the same exponent of n, rather than like a number like we might look at for the power series, this is a good candidate for when we want to use the root test. So here, what I'm going to look at, and let me change from my black color. We'll go back to this kind of pinkish magenta color, whatever it is. What I'm going to do is I'm going to say the limit as n approaches infinity of the nth root of the expression that we have. Now technically it should be an absolute value. Okay, so we'll put an absolute value of, oops, that should be an e to the power of n over n to the power of n. And obviously if I take the the nth root of that expression, I'm going to be left with the limit as n approaches infinity of just the absolute value of e over n. And of course, e is a constant, 2.718, and n, because it is working with a series, must be a positive whole number. So again, the absolute value isn't strictly necessary because everything that we have to work with is positive, but e divided by a significantly large number is going to approach a limit of 0. And so what I'm going to say in this case, because 0 is less than 1, not less than or equal to, but less than 1, less than, God, you did it again, where's my head? Less than 1, uh, so this series converges absolutely by the root test. And here's the next one, and I strongly encourage you to go ahead and see if you can work this one out independently and see what you're able to get. Now, some of you may be looking at it and say, well, okay, well, I'm not sure if the root test is something that I want to try to attempt here because I don't have something to the power of n in both the numerator and the denominator. And realistically, that's okay. It's fine. You could attempt to use maybe, I might try to do like maybe the integral test on this one, although the denominator is going to get a little funky when we work with that one. But we can definitely do this one with the root test because we do have one part of the sequence as something to the power of n. So here I'm going to say the limit as n approach infinity of, again, and if you don't want to do the radical, you could do something to the 1 over n power as well. That's the same thing as doing something to the nth root. And so here I'm going to have n to the third power over 3 to the power of n. And when I simplify this, of course, because the numerator isn't raised to the power of n, the radical doesn't really undo itself the way it will in the denominator. So this will give me the limit as n approaches infinity of, if you want to, you can write it as the nth root of n cubed. And in the denominator, the nth root of n of 3 to the nth power is going to just be a 3. Okay? Now the numerator may be a little bit hard to see what's going to happen. The nth root of n to the third power, what's going to wind up happening here. And you may want to just pick some numbers and play around with it. So start off with, I don't know, say 10, the 10th root of 10 to the third power. Then go to 1,000, the 1,000th root of 1,000 to 3 or to the third power, and then to the like 10,000. So you just pick bigger and bigger numbers that you want to play around with. You could look at this also as the limit as n approaches infinity, and we can rewrite the numerator as an exponent. We could write it as n to the what are we going to have here? 3 over n power, converting it into an exponent over 3. And you can maybe play around with it a little bit like that as well to see what the numerator is going to do. But as n goes towards infinity, as n gets bigger and bigger and bigger, the numerator approaches 1. So we wind up with 1/3 for the limit, which is fine. In this case, because 1/3 is less than 0, therefore, I can say this series, and I forgot my absolute value stuff there. Absolute value, absolute value. This series converges absolutely by the root test. And last example that we have here for what we're talking about for the root test. Clearly, we have the entire expression raised to the power of n, so this is a very clear candidate for wanting to do the root test. So here, we'll say the limit as n approaches infinity, as nth root of absolute value of n over 1 plus n to the power of 3 raised to n power. Well, of course, the nth root and the power of n are going to undo each other, and that is going to leave me with the limit as n approaches infinity of the absolute value, and in this case we're going to just wind up with n over 1 plus n cubed. Now here we don't necessarily need to use L'Hopital's rule, although I guess strictly speaking we should, because we would wind up with infinity over infinity. But if I do L'Hopital's rule, I'm going to wind up with 1 over 3 n to the second power. But either way, the denominator is clearly going to increase faster and larger than the numerator will. So in this case, the limit will be 0. And 0 is definitely less than 1. Therefore, this series will converge absolutely by the root test. So when we did the ratio test, we saw one of each type of possibility, where one where it converged absolutely, one where it diverged, and one where it was inconclusive. Now the root test follows the same thing. If the limit is less than 1, we can say it converges absolutely. If the limit is greater than 1 or infinity, we can say that it diverges. And if the limit was equal to 1 exactly, we could say that it was inconclusive to show convergence or divergence. But in this case, the 3 examples that we have all showed absolute convergence. So that's just the way it goes sometimes. So hopefully the root test and the ratio test, you have a pretty good handle on it at this point. Now this last little bit here, this is just going to be, okay, so we've talked about all kinds of different ways to show convergence or divergence. We've talked about the nth root test. We've talked about geometric series test, p-series. We've talked about direct comparison, limit comparison, whole bunch of different things. What is going to be the way that we want to, check for these things? Well, the probably the unsatisfactory answer that the best answer I can give you, but it's a little bit unsatisfactory, is just practice, practice, practice. The more you see these, the easier it's going to be to identify, oh, that's this type of series, that's this type of series, so that it makes it easier to show that when we're going to test for convergence or divergence. But some questions that you want to consider. Is it a special type? Geometric p-series, alternating, telescoping, you're really not going to see that a whole lot. It's kind of a special case, but you may see it as a telescoping series. Can the series be compared to a special type, meaning like a harmonic series or a geometric series or something? The nth term test is one of the easiest things to check for divergence. Remember, if the limit doesn't approach 0, or if the limit is going to be anything besides 0, that's an easy way to check to see that something is going to diverge. Can you apply the integral test, the ratio test, the root test? The integral test is probably my personal least favorite type of test to do, but it is possible. If we need to do it, we can do it. So here, and again, I strongly encourage you to see, can you look at these and determine what you would look at as an appropriate test in advance of me working it out. But barring that, let's go ahead and take a look at this. And I'm just for the sake of time, I'm not going to get real detailed in the answers that I'm going to write down. I'm going to just be kind of a bare bones expression about this. Looking at this one, pi over 3 to the power of n, we have some expression raised to the power of n. This one, Could we do the nth term test? I'm sorry, we just saw the root test, so this may want to say, okay, do we want to do the root test? Well, in this case, if we tried to do the root test, we're not going to have anything as n raised to a power, but this one hopefully is going to be jumping out at you. This one is geometric. A geometric series is very easy to tell if it's going to converge or diverge based on the common ratio. So remember, if the constant ratio is greater than 1, it's going to diverge. If the constant ratio is less than 1, it will converge. And in this case, r is greater than 1 because pi over 3 is greater than 1. So here I would just say that this one would diverge according to the geometric series test. This one here for B, this series, ideally, this one should be screaming at you. We can just check the limit on this one super easy. Because we just have one n term in the entire expression and it's in the denominator, that is probably something that you could look at for the nth term test. In this case, the limit is going to go to 0. But I need to check myself here. Because we only have the one term, in this case, the limit would go to 0, but the nth term test is inconclusive when we say the limit is equal to 0. The nth term test is really only going to test for divergence. So, I got a little excited there. I misspoke a little bit. But I still think we can use limits here. But in this case, really probably the limit comparison test is what I want to look at on this one. Okay. Remember, with the limit comparison test, we're going to compare it to, a smaller series. In this case, what I would compare the series to that was given to me is I would compare it to the series of just 1 over n. Again, we don't need to worry about the coefficients. We can just focus on the variable n in this case and whatever powers that they happen to have. And of course, this should be 1 to infinity. And I know that in this case, this is a divergent harmonic series. Harmonic series. So if I perform the limit test, the limit comparison test, and we get a value of an actual value, then either both series converge or both series diverge. So here I would perform the limit test, and according to the limit test, we would take the expression that we have, 1 over 4 n plus 1. And again, we're kind of doing the ratio. It's very similar to the ratio test, so I'm going to just multiply it by its reciprocal of n. And in this case, that's going to give me, and I should have my limit as n approaches infinity. That's going to wind up giving me a limit as n approaches infinity of n over 4n plus 1. And again, technically I should use L'Hopital's rule to show that, to avoid the indeterminate form, but we can justify that this is going to have a limit of 1/4. Okay? So, because, L, remember 0 less than L, L less than infinity, if we have some number that's greater than 0 but less than infinity, which we do, they both behave the same way. Therefore, I would say that in this case, both series will diverge by the limit comparison test. Now here is another one where again, in my mind, when I see it, it's like, okay, well, I can take the limit of that one really easy. In fact, that's basically what we just did on the last example. And I can show that the limit on that one is going to be 1/4. Well, the nth term test basically says if I get a limit of anything besides 0, we can justify that it's going to diverge. So that's what I'm going to look at here. Here I'm looking at the nth term test, where in this case, the limit as n approaches infinity of n plus 1 over 4n plus 1. And again, technically we need to use L'Hopital's rule to show that the limit in this case is going to simplify to be 1/4, but that's what the limit is going to be. And since 1/4 is not equal to 0, I can say the series will diverge. Like I said, it just kind of takes a little bit of practice. The more you work with them, the easier it'll be, but sometimes there's just going to run into problems that you'll think it'll work one way, and then you'll be like, well, that didn't work as well as I thought it would be, and you just got to try a different strategy. Start with what you know and work your way through it. Eventually, you'll come to enough conclusions that you're either going to be right or you're going to have to reassess the strategy that you try and pick something else. And you just pick away and pick away and pick away, and eventually you will eventually come up with a justifiable answer for what we're looking at here. Now, this one here, n over e to the n squared power. Man, maybe the root test could work, but if I take the root of the denominator, I'm still going to have a root overall. It's not going to, just simplify to be like e to the power of n or just e by itself. Let's see. Looking at this one, guys, I really think that the best strategy would be the integral test. Probably my personal least favorite type of test to perform, but remembering what we know about the integral test, is it continuous? Is the sequence continuous? And it is in this case. Will all of my terms be positive? Positive. They will, because n by a series must be positive, and anything squared, of course, is going to be positive. So we're going to have positive numbers. And overall, is the series decreasing? And as n gets bigger, the denominator is going to grow at a much quicker rate than the numerator will. So a larger denominator ultimately makes the value of the fraction drop, so it is going to be decreasing. So that means we got to use the integral test here. So let's see what we're going to end up with. So the integral test, the way that we're going to look at this is, let me go to a different color. We're going to say, let's see, try to remember what the integral test is going to be. So we're going to go from 1 to infinity as a function. So here I'm going to say this would be x over e to the power of x squared. And I'm going to look at this as a limit. Limit is not n. In this case, we got to pick something as an improper integral. Whatever the letter is that you pick doesn't really matter here. So we'll say as t approaches infinity. And let's see. And I forgot my dx there, but that's okay. So here, which way do I want to go here? We're going to look at doing some u substitution. So we're going to look at the limit of x 1 to t as x over e to the x squared. Let me put my dx here on that one. And in this case, if I do u substitution, if I say u is going to be the x squared term, u is going to be x squared, then that means du will be 2x dx, which doesn't match what we have here, so I got to say 1/2 du is equal to x dx, and now we have something that matches. So we're going to have a constant of 1/2 that's going to come out here. And let's see. Oh, you know what? I want to clean this up a little bit. Let me clean this up a little bit, because let's see. We're still going to basically have that, but let me clean this up a little bit. Sorry, if you need to erase anything, but I'm going to write it as x times e to the negative x squared power. So it's a little bit easier to do some integration with. So again, I'm still going to look at u in this case as being negative x squared, and du will be negative 2x dx. And so now I'm going to get a constant of negative 1/2 in front of my integral to give me x dx here. Okay, so that is going to give me my limit as n approaches infinity, negative 1/2, negative 1/2 times the integral from 1 to t. And in this case, it's going to give me e to the u du. And I wanted that to be in the numerator just because it would be a little bit easier to integrate. And so now when I integrate it, n approaches infinity, we still have the negative 1/2 constant, but the integration of e to the u is just e to the u. And we're going to evaluate it from 1 to t. And if we want to, we can really kind of say, okay, when let's see, do I want to rewrite my integral with u terms instead? No, I think we'll just leave it as 1 to t and not try to come up with a new interval. So we'll just leave it like that. And doing my substitution here, we're going to say the limit as n approaches, I keep writing n. I'm so used to writing n. These should be t's for the variable that I picked. So used to writing n for all the different types of tests that we have to do. 1/2. So I would say e to the t power. So in this case, when we do our substitution, we're going to get the negative x squared, but then I substitute the t in for negative x, so that'll give me negative t squared, and minus e to the power of 1. And no, that'll be, I think, did I miss something here? I got it. Should negative 1? Sorry. Let me pause for just a second and think about it. I think I'm seeing something that I need to correct here. Hold on a sec. Yeah, okay. My brain just kind of short-circuited a little bit. Yeah, when I take the 1 and I substitute it again, we're substituting it for negative x. So the negative x gets replaced with the negative 1. Oops, my pen quit working. With the negative 1 squared, and limit as t approaches infinity, negative 1/2. So we're going to get 1 over e to the t squared power minus 1 over e, basically. And as t goes towards infinity, this is going to go towards 0. And so we're going to wind up with the negative 1/2 times the negative 1 over e. So I'm going to get a positive 1 over 2e as my limit. And in this case, according to the integral test, because we approach a specific number, it's not a very nice number, but it's an irrational number because it approaches a specific number. So in this case, because we're approaching a specific number, this converges by the integral test. There we go. I knew we'd get through it. Moving on to example E, what we have here, ideally, the negative 1 to the power of n should be a tip-off that we're going to be having an alternating series here. So let me pick another color. Let's go green so it doesn't blend in with the purple so much. So this one here is going to look like as an alternating series based off of what we see here. Alternating series test. So the alternating series test, what we were looking for, we were saying basically, is the series going to be positive? In this case, yes, it will be. Again, when I explained that in the lesson, that's essentially not necessary. The only thing that we really need to know is the function decreasing, meaning as a sub n plus 1? Is it going to be less than or equal to a sub n as n approaches infinity, meaning is the series decreasing? And so here, if I kind of compare it with what I would be looking at as a comparison would just be 2 over, so here this would be negative 1 to the n plus 1 power times 2 over 3 times n plus 1 power plus 1. Is it going to be less than or equal to the given function of negative 1 to the n power times 2 over 3 n plus 1? And the denominator overall, here we're still going to have alternating powers of or alternating signs in the numerator, positive or negative. So the numerator really doesn't change, but the denominator on the left does grow faster than the denominator on the right. So the overall larger denominator in the fraction on the right will produce an overall smaller number. So yes, it is going to be decreasing. And the last thing that we really checked for, we would look to see, does the limit equal to 0? So here, the way that I would look at the limit in this case, the limit as n approaches infinity, we kind of ignore the negative, alternating term, and so I'm going to just look at it as 2 over 3 n plus 1, and that very clearly does go to 0. So I would say yes, this converges by the alternating series test. And we only got a couple more here. Oh, looks like it's time to leave class. That was that bell telling me it's time to go. So it's a couple more here and then we'll be done. Nth root, on this one here, this is very similar to the last example that we did on our root test. This one very much is going to look at a root test. So I'm going to say here, based on what we have, limit as n approaches infinity of the nth root of the absolute value n plus 1, nope, don't want that parenthesis there, n plus 1 over 3 n plus 1 to the nth power will simplify to be the limit as n approaches infinity of the absolute value of n plus 1 over 3 n plus 1. And again, technically I need to use L'Hopital's rule to avoid the indeterminate form, but we can see based on the rational expression that we have that this will have a limit of 1/3. And because 1/3 is less than 1, this converges by the root test. And the last one that we have here, the factorial, is a clear indicator that we want to try to do the ratio test on this one. So the ratio test here, I'm going to say the limit n approaches infinity of the absolute value of, here I'm going to say n plus 1 factorial over 3 to the n plus 1 power times the ratio of a sub n, which would be, or the reciprocal of a sub n, I should say, 3 to the power of n over n factorial. And let's see if we can clean this up a little bit. Remember, n approaches infinity. Let's combine our terms into ratios. Remember, n plus 1 factorial is basically the same thing as n plus 1 times n factorial, or just n really, but n factorial is what we have in the bottom of the other one, so let's make sure that they match. N factorial times 3 to the n power over 3 to the n plus 1 power. So what we're going to see, n factorial and n factorial simplify to be 1. 3 to the n power over 3 to the n minus 1 power, subtract the expressions, and 3 to the n powers are going to simplify with that n, leaving me just a 3 in the denominator. And keep going, and I'm going to wind up with the limit equals, let's keep our equal chain going, equals, limit as n approaches infinity, and we're going to wind up with n plus 1 over 3, which is going to have a limit of infinity. And based on what we saw for the root test, if the limit of the ratios was greater than 1, and infinity is definitely greater than 1, this series will diverge by the root test. I'm sorry, by the ratio test. So like I said, it takes a little bit of practice really to see which one you might want to use for any particular series that you're going to see. Now those of you that are following along with this lesson here for my class, you have this in your notes. If you just randomly came across this information on YouTube, here is kind of a, it's just kind of summarizing everything that we've done with our tests. Nth term really only tests for divergence, as long as the limit does not equal 0. Geometric series, telescoping series, that's kind of the real unique one. That's kind of the unicorn. You're not going to really see that much. P series test, if the P greater than 0, greater than 1, it's going to converge. If it's between 1 and 0, it's going to diverge, like our harmonic series. Alternating series test, we're looking for a -1 raised to some kind of a power of n, so that way you may also see an alternating series test would be like maybe with something of cosine of n times pi or something like that. So either sine or cosine may be used also as an alternating series, but usually it's going to be a -1 raised to a power. The integral test is something that you want to use if it's easy to show that it's going to be overall a positive series, that it's going to be a continuous series, and that the sequences are going to be diverging. And again, we're looking to see, do we wind up with a specific number to show that it's going to converge. If we wind up getting something like infinity, we would say it would diverge. And here we got the ratio and root tests, the ones that we just talked about. And then finally, the direct comparison test and the limit comparison test. Remember the direct comparison test basically said if you had a large series that diverges, then the small series must also diverge. If the small series converges, then the upper bound, the larger series, must also converge, or converge. And the limit comparison test, we saw an example of that, where if we do the ratio of the given series and kind of a simpler series that we can create, as long as we show that it's going to give me a specific limit value, we can show that it's going to converge. Okay, or rather, we say that both series will either converge or diverge based on what we know on something related to the other series. And boy, that's a lot of convergence and divergence tests that I hope you're going to have a good handle on when it comes time for your AP exam. But that's going to wrap it up for this lesson. Ladies and gentlemen, thanks for watching. Take care, and we'll talk to you soon.